All right, 2.2, graphs of functions. This one's a little bit of a quicker one. I think the only part that might be relatively new for most of you would be the second learning target, graphing a piecewise function. We talked about evaluating piecewise functions in the last section. Now we're going to graph them. So this first learning target is actually very, very brief. And I've listed or drawn functions, and they're really called families of functions. So we have the linear functions of the type mx plus b. And these are all, there's a nice table in your textbook on page 202 that has all of these drawn out a lot nicer than I've drawn them. And really the point of this learning target is to have a visual in your mind of when an instructor says, all right, we're talking about a linear function, that you have a visual in your mind of what the graph looks like. Okay, that's the point of this learning target. The next family of functions are called power functions, and that's your x squared, x cubed, x to the fourth. Those are power functions. You're all familiar, hopefully, with the quadratic function here. The shape of that graph is called a parabola. And then we have our cubic, is what this one is called. So those are your power functions. And again, simply when the point here is to have an idea in your mind of the shape of these power functions. So what does an x squared graph look like in general? What does an x cubed graph look like in general? The next family of functions are called the root functions. We have square root here, and we have a cube root here. And another family of functions are called reciprocal functions. We'll talk a lot more about these in chapter 3, the next chapter, section 3.6. And then you've seen this one, I'm sure, absolute value. It's a V-shaped graph. The equation looks like this. So your first homework problem, I think, is homework problem number 4. It's really just a matching question. It's going to give you a graph, and then you're going to match it up with the type of function it belongs to. So relatively easy, not much to do there. Most of the bulk of this section's homework is going to be in this next learning target, sketching a piecewise function. So we have piecewise function in 2 pieces, x minus 3 and 2x plus 1. Now before, this is something here that maybe you just watch and not start to write down yet. I want to try to illustrate something for you. So if we had one graph on which to graph this function, x minus 3, the first piece, x minus 3 is just a linear function with the y-intercept of -1, or -3 rather, and a slope of 1. So the whole function, x minus 3, looks like that, the graph at least. The other piece of that function, 2x plus 1, positive 1 is the y-intercept, and the slope is 2. So that function looks like that. That's both functions graphed in their entirety using all of the domain. But the difference here now with a piecewise function is x minus 3 is only going to be graphed for the values for which x is less than -1. And here's -1 right here. So again, what it means is that this graph right here, this is the graph x minus 3. Rather than the whole line appearing like it does now, the only part of this line that should be appearing is the part that has x values less than -1. Now what a lot of people like to do, and I'm okay if you do it this way, is at these boundary numbers, where these are the numbers at which the function switches from one rule to another rule, those boundary numbers, a lot of students will like to put a very light vertical line at that boundary, which right here, for example, splits the function up into 2 halves, the left half and the right half. And you've got to decide, well, which half do I need to keep? And in this case, we want to keep the half that fits in that portion of the domain less than -1 means to the left. So what we need to keep is the left part. I'm going to erase the right part of that. because the right part have values that are greater than -1, and we need to have values that are less than -1 for this piece of these. Now, one mistake that I've seen quite often is having the right symbol, and by that I mean, is it an open circle or a closed circle on the boundary? X has to be strictly less than -1, not equal to -1, which means we have an open circle right there. So this still is the function x minus 3, but it only includes x values that are less than -1. It doesn't have any x values that are greater than -1. Now, the other function that was drawn, or the other piece that was drawn rather, is 2x plus 1 right here for this rule. And I've got the whole entire graph 2x plus 1, but similar with the last piece, we don't want the whole piece, we want just the piece that has x values now that are greater than -1. So I still have that boundary right here. This is the boundary x equals -1. So if we look at that boundary, it splits that line up into two halves. It's got the left half and it's got the right half. We want the right half in this case, which is greater than -1. So we need to erase the part that doesn't fit, which is right here. And then on the boundary itself, x can equal -1 for this piece of the function, so we can use a filled in circle right there. And then we only have x values on this piece of the function. These x values are all greater than -1. So this is what the piecewise function actually looks like. That was a long way of graphing it. What most students do, rather than graphing both lines in their entirety and then trying to erase, because it gets messy and some students like to write in pen. So what some students like to do is just evaluate pieces of the function using the given x values. So what I mean by that is, if we look at just this top piece, I'm going to evaluate a couple of x values using this inequality into that rule. So, and technically x is not supposed to equal -1, it's just supposed to be less than, not less than or equal to. But for the purpose of graphing, you want to have the value of those points at that boundary. So I am going to evaluate -1. So for this piece, I'm going to evaluate f of -1, and then I want values that are less than that. So f of -2, f of -3. So f of -1 would be right here if I plugged in -1. -1 minus 3 is -4. If I plugged in a -2, I would get -5. If I plugged in a -3, I would get -6. So that gives me a couple of points to plot, -1, comma, -4. But remember, -1 doesn't really exist in this piece because x has to be strictly less than -1, so that's where we would place the open circle. And then we'd have -2, comma, -5, and then we'd have -3, comma, -6. So that gives me the direction for that piece. And then for this piece of the function, I can evaluate a new set of values. So I'm still going to evaluate at the boundary number, which is, I'm going to evaluate f of -1, and then I need to go greater than -1, so I need to evaluate f of 0 and f of 1. These are all values greater than -1. So if I plug -1 in here, I'm going to get 2 times -1, which is -2. -2 plus 1 is -1. If I plug in a 0, I get 0 plus 1, which is 1. If I plug in a 1, I get 2 times 1, which is 2. 2 plus 1 is 3. So -1, comma, -1, and this is that boundary number, so you got to think, is it an open circle or a closed circle? And in this case, since it's an equal to, that's a closed circle. Then we have 0, comma, 1, and then 1, comma, 3. So there's the same piecewise function. In this case, we graphed the function by plotting points rather than graphing the entire line and then trying to erase portions of it. And another thing to keep in mind, like I mentioned in section 2.1, these are still functions. It's a piecewise function. And And this is something that we will talk about a little bit later on, but some of you might be familiar already with what's called the vertical line test. These graphs must still pass the vertical line test because they are functions. And that's why it's important right here, for example, that one of them is an open circle and one of them is a closed circle, so it still passes the vertical line test. Okay, so as an example for us to practice, we've got another piecewise function here. This one has 3 pieces, so there's going to be 3 different little graphs graphed on here, or 3 different pieces of a graph that all belong to the same function. So I'd recommend that we do the same thing that we did in the problem above. We evaluate each piece using several values of x. For example, this top piece, I want to find f of, first of all, you always use the boundary number. So I'm going to find f of -3. I'm going to find values now less than that, so f of -4, f of -5. This one's a little unique. The rule of this function is regardless of what the x value is, or the input, the output is always going to be 4. The output is never going to change from 4. So again, regardless of what we plug in for x, the output is always going to be 4. So if I plug in a -3, I'm going to get 4. If I plug in a -4, I'm going to get 4. If I plug in a -5, I'm going to get 4. I'm always going to get 4 as the output. Now, since this was the boundary number, I'm going to decide if that's an open circle or a closed circle, and because it's less than or equal to, it's a closed circle. So a closed circle at -3, 4, and then a closed circle at -4, 4, and -5, 4. So that's just completely horizontal line. It's got a slope of 0 with a closed circle on that boundary point of -3. Now, here in this middle piece, we have 2 boundary numbers. We have a boundary number of -3, so I need to figure out f of -3. And we have another boundary number here of +2. This is called a bounded interval, where it's bounded on either side. It has a left and right bound. So I'm also going to find f of 2. But in between, I can figure out a couple of intermediate values between there. I could do f of -2, f of -1. That should be enough. You don't need too many points here. So all of these inputs are going to be plugged into that rule, input squared, or x squared. So if we have an input of -3, that means -3 squared, which is 9. And that's a boundary number. -3 was one of our boundary numbers, and in this case, x has to be strictly greater than, not greater than or equal to. So that's an open circle at -3, 9. That's an open circle right here. If you plug in a -2 squared is 4. So -2, 4 right here. If you plug in a -1, we get 1, 0, 0, and then f of 2, if we plug it into 2, we would get 4. And remember, 2 was one of our boundary numbers here, so we check is it an open or a closed, and because it's less than or equal to, that's a closed, so 2, 4. So this piece of the graph is just a portion of a parabola, or a quadratic function, between -3 and +2, right there. Now the last piece here, the bottom piece, we're going to evaluate just a few more values of x into this function piece 3x plus 2, and we're going to use that boundary number. So I need to figure out f of 2, and then any values greater than that now. So f of 3, f of 4, and these are going to be plugged into this piece. We're using that rule, so 3 times x now becomes 3 times 2. If I plug a 2 in here, that's 6. 6 plus 2 is 8, and since it's a boundary number, I check is it an open or a closed circle. Greater than and not greater than or equal to means open, so 2, 8 would be an open circle right there. Now 3 times 3 is 9. 9 plus 2 is 11, so 3, 11 way up here. And then 4 times 3 is 12. 12 plus 2 is 14. So 4 comma 14 would be up here. So that piece of the function looks like that. Okay. So that brings us now to our last learning target, which is to determine if a relation is a function. Now, a relation is just a mathematical rule, and we can think about relations several different ways. A relation could be an equation, a relation could be a graph, a relation could be a table of values, an XY table of values. Those are all relations, but not every single relation is a function. Remember, a function is a rule for each input. There is exactly one output. So I've drawn two different graphs here. These are both relations. This one, however, is a function. This graph is a relation that is not a function, and the reason is, this one on the right is not a function, is it doesn't follow this rule of for every input there's exactly one output. What I mean by that is, let's take this input right here. Let's say, for example, that this is an input of 4. Well, if I plug in 4, I get two different values of y, or two different output values that have that same input. So maybe 2, and maybe this is a 5 up here. So for one single input, 4, I get two outputs, 4 comma 2 and 4 comma 5. So it's not a function. One simple test, which I'm sure many of you have seen before, is what's called the vertical line test. So if I drew a vertical line through this relation, the vertical line passes through that graph twice, meaning one input has two different outputs or several outputs. And so this is a rule that you can use if you have a graph to determine if a relation is a function. If it passes the vertical line test, it's a function. This graph passes the vertical line test. Any vertical line that I draw through this function only passes through the function one time, so it passes the vertical line test, hence it is a function. So the vertical line test is a quick visual way to verify that a relation is a function graphically, but we also need to consider that functions or relations can be represented using equations. So the vertical line test doesn't help us there unless we want to graph everything, but sometimes that takes a little bit longer than is needed. So the question is, does 3x squared minus y equal 5 define y as a function of x? And really all we need to do is, if we're interested in if it defines y as a function of x, we need to rewrite the equation in terms of x. We need to write the equation y in terms of x, so solve for y, essentially. So if we got y by itself, we would, well, I guess what I would do is add y to that side and then subtract 5 to that side. So we would get y equals 3x squared minus 5. Now, we're not going to graph this. We can reason our way through this using the definition of a function. Remember, the definition of a function is for each input, you get exactly one output. So let's just consider a couple of different values of x. If I plugged in a value of x, it's going to be squared. You multiply it by 3, then you subtract 5. Is that ever going to produce two different values if you plug one number in for x? For example, if I plug in a 0, I get 0 squared, which is 0. 0 times 3 is 0. 0 minus 5 is negative 5. So if I plug in a 0, I get negative 5. One input gave me one output. Any value I choose for x to plug in as an input is only ever going to produce one output for y. So this is going to be a function. So the answer is yes. That equation 3x squared minus y equals 5 does define a function y as a function of x. Now, what about x squared plus y squared equals 4? We're going to do the same thing. Does it define y as a function of x? What we need to consider is, what is the equation written kind of in this form where we have the equation solved for y? So what we would do is subtract x squared, and then use a square root on both sides. And what that does, and this is one thing that students like to forget, I even from time to time will forget, but whenever you use a square root in the process of solving an equation, you have to put plus or minus. So now the question is, does this define y as a function of x? I mean, you can use a similar type of reasoning. If I plugged in any random number for x, for example, if I plugged in a 0, then 0 squared is 0, 4 minus 0 is 4, and the square root of 4 is plus or minus 2. So what we actually got is, when I plugged in x equals 0 for the function value, or for y, I got two different values, -2 and +2. So this doesn't follow the definition of a function. One input actually gave me two outputs. One input gave me two outputs. So the answer here is no, it's not a function of x. So on your homework, when they are having you evaluate equations of relations and asking if it's a function, the way that you do it is get y by itself, and then if you were to plug in any number for x, what's the result? Do you get one number out of that, or do you get several numbers out from that as outputs? And that can help you determine whether the relation is a function of x. And that should finish us up here for lesson 2.2. Just quickly review here. The first part of the lesson really was simply getting familiar with families of functions, so that if I were to mention, hey, we're talking about a square root function, that you have a visual in your mind of what those graphs look like. Or we're talking about an absolute value function, you have a visual in your mind of what those graphs look like. The next part was graphing piecewise functions. And piecewise functions are best done, as the name suggests, piece by piece. So I took the top piece, evaluated several values of that top piece, and graphed those here. Then I took the middle piece and evaluated several pieces of that middle piece, or several points of that middle piece, and graphed it here. And again, always graph or evaluate the boundary numbers, so these numbers, and then decide whether they represent open or closed points. That's graphing a piecewise. And then we talked about determining if a relation is a function. We've got the vertical line test to test graphs. And then if we're given the equation, we write the equation y in terms of x and input x values to see if one x value gives us either one y value or several y values.